Alright, welcome back guys to part 3 of our Calculus 3 final review. This is the last part. This is it. After you get done with this, you should be done studying for Calculus 3, your Calculus 3 final, and then you can move on to something else that you want to do with your life, alright? But in this video, we're going to be tackling vector calculus. Now, vector calculus is pretty much the hardest part of Calculus 3. I know some people have trouble with multiple integrals, but vector calculus generally takes the cake as the hardest part of Calc 3. So what we're going to do in this video is I'm going to go through each of the topics that you cover in vector calculus, line integrals, surface integrals, Greens Theorem, and Stokes Theorem. And I'm going to talk to you about what these things actually are, what they're helping you find, and different things like that. And then of course I'm going to be doing examples with those things as well. All right, so let's head right down into the iPad here, and this is kind of the screen I've had for the part 1 and part 2 videos. In part 1, we covered kind of all the derivative stuff, and we covered like quadratic surfaces and equations of lines and planes, so kind of all the intro stuff and then derivatives. In the last video, the part 2 video, we did multiple integrals, so we did double, triple, we did change of variables. And in this video, we'll be covering basically everything vector calculus, okay? And I do have timestamps for each one of these topics, so if you are struggling on a certain one of these topics more than another, you can just go right to the timestamp. All right, so without further ado, let's hop into our first one, which is line integrals. Okay, the first thing is, what is a line integral actually like? What are we integrating? Well, we're integrating a three-dimensional curve, and I have a picture of this on the right here. Right over here, okay? You have some curve in 3 dimensions, all right? And you're finding the area under that curve, okay? That's essentially what you're doing in a line integral, and of course there's other applications for it as well, but that's kind of the general idea of, a line integral. That's all you really need to know about it. And that'll just help you get an idea of what's going on with a line integral, right? It'll give you a little bit of purpose. All right, so that's the idea of what a line integral actually finds. Now, there's a couple different equations for line integrals, and this kind of all depends on what you get. Okay, you might have, just the classic line integral of a function of x and y, and then you have a ds on the end. Okay, so it's kind of like a differential of like arc length, I guess is what you could say, because that's essentially where this ds becomes this piece over here, okay? And as I noted, this comes from arc length, okay? This whole thing, you can kind of remember the arc length equation looks something like that, right? So that's what that's where the ds comes into play. But other than the ds, this f of x, y, you just parameterize that so you have a function of a single variable. And then you're able to do, a single integral with that, because now you have it as a single variable, okay, with respect to, dt. So that's basically the first equation. There's another equation where you have, again, your function of x and y is parameterized as, with our parameter being t, and this dx, it becomes x prime t dt. So that's basically a u sub. Okay, and that's the same thing if you had a dy here. This would now just be y prime of t dt. Okay, you have our last equation here. We have a line integral. We have now like some vectors going on here. So let's say you have a vector f. You basically have the same exact thing as what I just showed right here, but now it's with vectors instead. Okay, so it's the same idea. Now, here's an idea for multiple integrals that I wanted to share with you quick. If the function that you're integrating is just 1, then you're essentially finding the length of the curve. Okay? Now, remember in the last video when I talked about a double integral, right? A double integral gives you the volume, but if your integrand is 1, then it's going to give you the area, right? Because you talk about volume equals length times width times height. If your height, right, your integrand is just 1, then you just have length times width, which is area. Okay? So in the same way here, All right, and you can kind of think about it. If your integrand, if that curve that you're in 3 dimensions that you're integrating under is just 1, right? Well, that is just going to give you the length of the curve, right? Instead of having an area, you're just going to have, well, let's put it this way. Area is length times width, right? If your length, which we'll kind of think of as like the height, is 1, then you just have the width. In other words, you have the length of that line, okay? So hopefully that makes sense. That's just an idea I wanted to pass along quick before we begin our example, which, well, we want to find the line integral as the integral over the curve C of x plus 2y dx plus x squared dy, where C is the 2 line segments from 0, 0 to 2, 1 and from 2, 1 to 3, 0. Now, before I actually get into start like going through this problem, this is a line integral with dx and dy in there, so you might want to get practice with a line integral with ds in the integrand, because that's a different formula. Now you're using the arc length formula, so maybe you want to get some practice with that as well. I'm not going to be doing that in this video, but it might be something to look into if you're struggling with line integrals. Okay, so we're essentially just going to be using this formula right here. Okay, so it's this idea here. Now what we're going to be doing, okay, first, let's just realize that we're going to have 2 separate integrals, okay? This integral will just get broken up with our 2 curves, which are line segments. So C1 is from 0, 0 to 2, 1, and C2 is going to be from 2, 1 to 3, 0. Now that we have that out of the way, what we can do is kind of just rewrite, just so you have an idea of what we're about to be doing here. Okay, so this line integral can get broken up into 2 separate line integrals. So I'll copy and paste this twice. Okay, and what this essentially is, so we have equals plus, we're going to integrate over C1, and then we're going to integrate over C2. You add those 2 things together, and you are essentially integrating over your entire C, which is C1 plus C2. Okay, so now what we have to do is, well, actually parameterize this thing. Okay, because that's really all we have to do with this formula here, which I can kind of drag down just so I don't have to keep scrolling back up. Okay, so this is what we're going to be modeling. Okay, so let's start with C1. Okay, so for our parameterizations, okay, for C1, we have actually, I'll look up here for that. For our parameterizations, you can see that you just look at what C1 actually is. So C1 is a line segment for in X, it goes from 0 to 2. So we can essentially call X 2t. Okay? And we can call Y t because it goes from 0 to 1. So if we're saying that t goes from 0 to 1, then we essentially have x going from, well, if you plug in 0, you get x equals 0. If you plug in 1, you get x equals 2. So that's why I parameterized it like that. Okay? So hopefully that makes sense how we actually come up with the parameterizations. I'll come back to that when we actually have to parameterize C2. Okay? So now that we have that all set, what we're going to do is just end up plugging that in. So trying to get the best view on it, what I'll do is I'll zoom out here so you can actually see it. So we have the integral over C1, okay, and that's of x plus 2y dx plus x squared dy, okay, and well, C1, that's just from 0 to 1 on the t, okay, so we know that x is just 2t, y is t, so 2 times y is 2t, dx. Okay, now remember, in this formula, this dx becomes x prime t dt. So we're essentially doing a u substitution. So if x is equal to 2t, that means that dx is equal to 2 dt. Okay, so that's what we're going to plug in for dx right here. So we have a times 2 dt. Then we have plus x squared just becomes a, well, since x is 2t, this becomes a 4t squared. And then we have dy. So what is dy? Dy is just dt. So this becomes just dt. Okay? So that's, simple enough, right? We go through here, and now I can zoom back in. Let's simplify this, and then we're going to integrate it. So we get 4t times 2 dt. So actually, I can just simplify that to be 8t. So we have 8t plus 4t squared. We can just factor out the dt, right? And now we just have a nice little integral. This becomes 4t squared plus a 4 over 3t cubed, evaluated from 0 to 1, which is just going to be 4 plus 4 over 3. And, well, that'll just be a 16 over 3. Okay? So it's kind of like a step-by-step, all right? You first start off by parameterizing your curve. We did that, okay? We found x, we found dx, we found y, we found dy. We plugged all those things in, and we integrated, and then we evaluated, okay? So that's all really that happened with our first curve. We do the same exact thing with our second curve. Okay, so we will have integral over c2 of x plus 2y dx plus x squared dy. And now we'll just have to parameterize again. Okay, and so I don't have to keep going back and forth. I will bring the c2 down. Okay, so there is c2. So if we're going to parameterize c2 on the interval 0 to 1 in the t, what is x going to be? Well, x, if it's going from 2 to 3, it'll just be t plus 2. All right, and that means that dx equals dt. And y, if it's going from 1 to 0, that means it essentially is going to be negative t plus 1. So dy equals negative dt. Okay, so there you go. Those are our 4 things that we're going to be plugging in. So we can write this as the integral from 0 to 1 of x, remember, is t plus 2. This is plus a 2y, which is going to be negative 2t plus 2. That is all times dx, which is dt. And then we have plus x squared. And x squared is just going to be t plus 2 squared. And then we have a dy is negative dt. So we can essentially just write this as a minus and then have a dt. Okay? So now we just gotta simplify this baby, because this is a mess right now, and what we'll end up getting is a negative t plus 4 dt minus a t squared plus 4t plus 4, and we have a dt right there. So combining, we get a negative t squared. We have a minus 4t minus t is minus 5t. Then we have plus 4 minus 4. So that's all that just cancels out. And then we have a dt there. We integrate. So we get negative t cubed over 3 minus 5t squared over 2. And we evaluate that from 0 to 1. You'll get a negative 1/3 minus a 5/2, which when you simplify this thing, you're just going to get, I'll just give you the answer here. It's going to be a negative 17 over 6. Okay? Combining that with our previous answer that we got in C1, 16 over 3 minus 17 over 6, which is just going to be equal to the whole integral over C, is just going to be 32 over 3 minus 32 over 6 minus 17 over 6, which is 15 over 6, divide by 3 over 3, and you get 5 halves. So 5 halves is going to be your answer. Okay? So I know that was a lot, and I just honestly want to make sure that you are comfortable with all this. So let me recap line integrals real quick. So remember, a line integral, we are finding the area under a 3D curve. Okay, we have a number of different equations depending on what kind of situation you have. I mentioned maybe you want to check out a integral that has ds in it rather than dx and dy. Okay, and when we went into our problem here, we were given our integral. We had our two line segments, C1 and C2. Okay, and what we did was we parameterized C1 and C2. Okay, so that's what we plugged into our integral. Once we parameterized, all we had to do was integrate and evaluate. Okay, so you can see here we plugged in our parameterizations for C1, we integrated, and we evaluated. Okay, so that's the idea with line integrals. Okay, hopefully that doesn't seem too confusing to you. All right. Moving on to the fundamental theorem for line integrals. Okay, this is the next thing we'll be focusing on. And basically what it is, it's a really nice way to quickly evaluate line integrals. It comes from the fundamental theorem of calculus, unsurprisingly. And the equation that you use for the fundamental theorem of line integrals, like what it actually is you have the integral over some c of a gradient of f dot dr. And that's equal to that original f, right? So it's just f of r of b minus f of r of a. Okay, and there are restrictions though, because I mentioned that this has to be a gradient gradient. So this only works if you have an antidifferentiable integrand. Okay, and of course that would mean that it would have to be continuous as well. So if you don't have a antidifferentiable integrand, right? Let's say that you tried to do an antiderivative and it doesn't work. Well, then you know that Greens Theorem and or other stuff like that, that's going to be your better bet. Okay, but if you do have an antidifferentiable integrand, okay, then what you're going to want to do is stick with the fundamental theorem for line integrals, because it's really easy compared to some other methods. Okay, so let's do an example. Let's find the integral over c of f dot dr, where f of xyz equals yz I hat plus xz j hat plus xy plus 2z k hat. Okay, and c is going to be the line segment from 1, 0, negative 2 to 4, 6, 3. Okay, so that's we only have to deal with one curve this time. We don't have to deal with anything other than like having a C1 and C2 and all that stuff. Okay, so what I'm going to do is I'm going to undo the gradient operation, because we want to see if f is conservative. So is f conservative? Which means, can we take an antiderivative of it? All right, can we take an antiderivative of our f? So we're going to undo the gradient operation. Okay, that's how we take an antiderivative. So first off, let's take our first entry, yz, and what we're going to do is integrate it with respect to x, because it's in the x spot. So we'll have yz dx, and well, that's going to equal xyz, and other things that could have been included. You could have had some function of y and z, and that would have, if you took a derivative of this piece with respect to x, that function would have went away. Okay, so that's why I'm going to put that there. Now let's integrate our y piece. That's xz dy. Okay, and if you do that, you get xyz again, and now you'll have some function of x and z. And if you integrate your last piece, which is xy plus 2z with respect to z, what you're going to get is a xyz plus z squared. And then you could have some function of x and y. So comparing all this stuff, other than the main xyz, right? So we know xyz is in everything. But what isn't in everything is the z squared. Okay, so this z squared is exactly what these pieces are. And this piece, if you're wondering, just doesn't exist, right? If it did exist, then it would be apparent being like an added like x squared here, and that's the whole point. So really what's going on here is that the antiderivative here, you'll see that constant ends up being z squared. And like I said, this thing we can see as shown here and here, it doesn't exist. It's zero essentially. Okay, so now that we know that this thing is conservative, right, it has an antiderivative, and that antiderivative is, we call it f of x, y, and z, is xyz plus z squared. All we have to do is use the fundamental theorem of line integrals. Okay, so let's write this down. So c, the integral over c of f dot dr is equal to f of r of b minus f of r of a. Okay? And so now, what's our b and our a? Well, those are just our points, right? If I bring them down, we can call this a and call this b, and there you go. Okay? So what we're going to have is xyz plus z squared evaluated from the point 1, 0, negative 2 to 4, 6, 3. Doing that out, we have 4 times 6 times 3 plus 3 squared. And that is going to be minus 1 times 0 times negative 2 plus z squared is going to be negative 2 squared, which is 4. Okay, so we get equals 4 times 6 times 3 is 72. 3 squared is 9. And then we have minus 4. So we get 77. All right, so that's how easy the fundamental theorem of line integrals really is. All you have to do is you find the antiderivative and plug it in, and you're good. That's all it really boils down to. Okay, so that's really nice, but remember, you can only use that if you can actually undo that gradient operation. Okay, if you can't, right, you have some non-conservative vector field or something like that, well, now you need to use what we're going to talk about next, and that's Greens Theorem. Like I said, that's great for non-conservative vector fields. Now, you can also use Greens Theorem for conservative vector fields, but it just, Greens Theorem kind of specializes with non-conservative vector fields, or just a vector field that is really disgusting to undo the gradient operation with. Okay, so that's when you should really be using Greens Theorem. And the equation for that, let's say you have a vector field with components PQ. Well, you have your line integral over C of f dot dr equals the double integral over some planar region D of dq over dx minus dp over dy dx dy. Okay, and I also wrote that you can represent that force, that vector field as pdx plus qdy. Okay, and kind of the whole idea behind that is if you're representing f as pq, well, this was a derivative with respect to x, and this was a derivative with respect to y. That's how you get your vector field. Okay, So that's the idea there. Now, the restriction with Greens theorem is that it only works for 2 dimensions, okay? Now, there's a 3-dimensional version that's called Stokes theorem. We're going to do that later. That's a little more messy, okay? But yeah, this only works for 2 dimensions, so that is a restriction that you will have to deal with, okay? Now, where do we get Greens theorem from, okay? Well, let's start off with the fundamental theorem of calculus, okay? I'll start off with that down here. We have f of x equals the integral of f prime of x. Okay, that makes sense, right? We're taking an integral, we have a derivative. Those offset. Now, with Greens theorem, we're going to start with the fundamental theorem of calculus, and we're just going to integrate again on each side. That gives us Greens theorem. Here's how that relates. You can see here that we have a single integral of f right here, and on the right-hand side, we have a double integral of, this is just f prime. Okay? So that's really the whole idea with Greens theorem. That's where that comes from. It's just a kind of extension of the fundamental theorem of calculus. You're going to realize that all of these things in vector calculus are literally just extensions of FTC. That's pretty much it. Okay? Let's do an example with Greens theorem. We're going to be doing the integral over c of y plus e rad x dx plus 2x squared plus cosine of y squared dy. Okay, c is going to be the boundary of the region enclosed by y equals x squared and x equals y squared. So the first thing we might as well do is get an idea of what that c looks like. Okay, so we'll draw our axes here. I'll do this this is only going to be relevant in the first quadrant, okay? So actually I won't even draw it in any other quadrants. There's y equals x squared. And then we'll do x equals y squared. Okay? So there's x equals y squared. And you can see now that the intersection is completely in the first quadrant. So then c is going to be the boundary of that region enclosed. So c is there, and you can make it go counterclockwise. Okay, so there is your c. Now that we have that, what we can do is start using Greens theorem. Okay, so let's bring down this integral. Copy, paste. Now what we can do with our integrand is we can represent this as, remember, f is equal to pq, right? Those are the components of our vector field. So what we're going to do is just make these components. So y plus e to the rad x is our first component, and our second component is 2x squared plus cosine of y squared. Okay, there you go. So what we're going to do is we're going to take a derivative of q with respect to x. We're going to take a derivative of this with respect to x. Okay, because remember that Greens theorem, I should probably restate this as well. We have dq over dx minus dp over dy dx dy. So we take a derivative of q with respect to x. Okay, if we take a derivative of that with respect to x, that cosine of y squared goes away, and we're just left with 4x. Taking a derivative of dp of p, we get, well, that e to the rad x goes away, and we just have the derivative of y, which is 1. Okay, so there you go. There's your two derivatives, and now we just plug that in and go from there. We have dq dx is 4x, and then dp dy is 1. So dx dy. Now what's our region of integration? Well, remember, it's that that curve C, right? So remember, this intersection point is at 1, 1. Okay, and what we can just do is say that x goes from 0 to 1. So we'll say that x goes from 0 to 1, and then we'll say that y, well, it goes from x squared to rad x. Okay, and that needs to be reversed. So I will reverse that in the next line. Okay, so we'll write it as the integral from 0 to 1, integral from x squared to rad x of 4x minus 1 dy dx. So if we integrate with respect to y first, what we'll get is 0 to 1, then we have 4xy minus y evaluated from x squared to rad x. Okay, and then we have dx on the outside. So what we end up getting is the integral from 0 to 1 of, this will be a 4x to the 3 halves minus a x to the 1 half minus a 4 times x cubed plus a x squared. Okay, so, and then we'll have a dx on the end. Now we can just integrate and get 4 times 2/5 x to the 5 halves minus a 2/3 x to the 3 halves minus x to the 4th plus x cubed over 3 evaluated from 0 to 1. This evaluation is pretty quick because we just have the 0 making everything go away. That 1 stays and just gets rid of all the x's, and we have 4 times 2 over 5 minus 2/3 minus 1 plus 1/3, and so we get a 8 over 5 minus, we have a minus 2/3 minus 1, that's minus 5 over 3 plus 1/3, that's minus 4 over 3. Getting common denominators here, we get 24 over 15 minus a 20 over 15, which gives us just a 4 over 15 as our answer. Okay? So, that's definitely not that bad either. You just have to remember, okay, what's your boundary of your region? You gotta put that as your bounds, and that's something that we worked a lot with in double integrals. In the last video, we had to come up with those bounds of integration, and I think that's honestly the hardest part of this. So now we're going to begin with curl and divergence, and these are probably the nicest things that you have to deal with in vector calculus. I mean, the cross product in curl sucks, but it's it is what it is. The equations is just that the curl of f is del cross f, and the divergence of f is del dot f. Okay, so pretty easy to remember. And when I was in Calc 3 and I was doing curl and divergence, I just didn't know what they meant. Here's kind of what curl and divergence actually are. Curl is how much your vector field is curling, and divergence is how much f is actually diverging. Now, we'll see later when we talk about divergence theorem that divergence of f is really, really nice for like flux computations and things like that. So if you're a physics student, you might be able to see how that relates to your divergence, how much something's going outward, kind of relates back to flux. Okay, you can kind of think of Gauss's law or something like that. Okay, so let's do an example quick, just finding the curl and divergence of a vector field. We'll first do the divergence just because it doesn't have the cross product. So we'll do the divergence of f, which equals del dot f. And so we're going to be dotting. Remember, del is just partial derivatives. Okay, and that's going to be dotted with f, which is e to the x sine of y, e to the y sine of z, and e to the z sine x. So it's going to be d dx of e to the x sine y plus d dy e to the y sine z plus d dz e to the z sine x. Okay, so let's take those partial derivatives. We just end up getting sine y This is going to be e to the y sine z, and this is going to be e to the z sine x. Okay, and that is the divergence of f, of your vector field. Okay, next we'll do the curl of f. Okay, and the curl is just del cross f. So now we actually have to do a cross product, which definitely isn't the nicest thing in the world to have to do. Let's set up a matrix. We have I hat, j hat, k hat. We'll have our partial derivatives here. And then we'll have our components below. And I'm sure you guys have already dealt with cross product enough, so I won't bore you too much with it. Okay, we just have our I hat vector, which is going to be d dx of, sorry, not d dx, jeez, all right, d dy of e to the z sine x minus d dz of e to the y sine z. Okay, and then we have minus j hat times d dx e to the z sine x minus, we'll have a d dz of e to the x sine y. Lastly, we'll have our k hat vector, which is going to be d dx of e to the y sine z minus d dy of e dx sine y. So now, actually making this look a lot nicer, we're going to have, I'll cross out everything that becomes 0 with a green. So d dy of e to the z sine x, that goes to 0. D dx e z sine x, that does not. D dz, that goes to 0. And that will go to 0. Okay, so we're just going to be left with, let's see, a negative e to the y cosine z as your I hat vector. Your negative j hat vector will be you'll be e to the z cosine x, so that'll be negative e to the z cosine x. Your k hat portion will be just negative e to the x cosine of y. Okay, and there you go. That is the curl of f. So now we're going to move on to surface integrals, and before we begin, I got to admit that surface integrals were probably my least favorite topic in Calculus 3. I honestly found them to be so much more difficult than like anything else in Calc 3, because I just couldn't, like, it feels like everything that I was learning in Calc 3 that I didn't understand all piled up in surface integrals, and it just made for an awful time. But I'm going to explain it to you so you don't have the same problem. Basically, as kind of a quick gloss over of surface integrals, we're integrating over a surface. Okay, that's the whole idea of a surface integral, and our function, you can think of it something like a density function, where you get the density at each point on the surface. Okay, and if we integrate, okay, with a surface integral, we can find the mass of that surface. So that's kind of the idea there. And the equations, well, there's two that we're going to be using in this problem, and I believe I think these are the only two equations for surface integrals, but you can correct me if I'm wrong. We have, first off, that the double integral over a surface of a function of 3 variables times ds, okay, this thing, equals the double integral over a planar region D, okay, of f of r of uv, which means that we're going to transform this 3 variable function into just a function of 2 variables, essentially. Okay, and then we're going to be multiplying by this RU cross RV, which I will talk about in just a second here. That's going to be another, that'll be another story, okay? And the other equation that we have here is, well, we have a surface integral, and that's equal to that double integral of f of xy, and then we have g of xy. So this is when you can represent z as a function of x and y, and then in this case, you have a nasty square root after that, but it's not the worst thing in the world, I guess. Now, the question that we have here is asking us to find the double integral over the surface S of z ds, where S is a surface with sides S1 given by the cylinder x squared plus y squared equals 1. Okay, and I have all this jotted down, by the way. But so S1 is the sides of this cylinder, but you'll see in a second. With bottom S2 given by the disk x squared plus y squared is less than or equal to 1 in the plane z equals 0, and with top S3, which is a part of the plane z equals 1 plus x that lies above S2. So when you graph all those things, okay, you get this guy right here. Okay, so and make sure you can, of course, graph that and go through that. Okay, that's going to be very important. But what we're going to have to do here is, well, since we have our surface split up into 3 different surfaces, we're going to have to basically just add these together, right? So we're going to have to find the surface integral for S1, S2, and S3 separately. Okay, so this is going to be a pretty rough problem, but you shouldn't get any surface integral problems that are longer than this or harder than this. Okay, so to start off for S1, okay, now for S1, that's this gross side region right here. Okay, this is the side of this surface. All right, and well, that's gonna be kind of hard to deal with, like when we talk about like the bounds of an integral that would cover that area. So what we're going to do is parameterize it in a way that's related to polar. Okay, so I'll put it that way. How we're going to do it is we're going to say that x is equal to cosine theta and y is equal to sine theta. All right, so we're just setting up a circle. Okay, and z is just going to stay as z. Okay, so actually kind of like mirroring cylindrical in a way. But what we just did is formed a function of only 2 variables. Okay, so we have just cosine, we have just theta and z. Okay, now we can talk about the bounds for these variables. We know that theta would have bounds from 0 to 2 pi, since that cylinder is all the way around. We also know that z, right, the plane is the top bound, and z equals 0 is the bottom bound. That's said in the problem. So x is now cosine theta. We can rewrite this thing as 1 plus cosine theta. Now, since we have our bounds, we really only have one step left in this integral. Let's set it up and you'll see what I mean. We'll say that the double integral over the first surface of z ds is equal to the double integral over some planar region d1, so planar meaning flat, right, of z, okay, because z just stays the same, of r theta cross rz. That's going to be our cross product. Instead of ru cross rv, our variables are theta and z, not u and v. So that's going to be how we set that up. Okay, and then we're going to have dA on the end. All right, so now we're going to have to find that r theta cross rz thing, and basically what you have to understand about that is it's a cross product, okay, and you have your r theta. We'll put our r theta right here, the entries of that vector, right, and we'll put the entries of our rz vector below that. Okay, then of course the absolute value signs means we're going to have to find the magnitude. Now, what this is saying, well, if we took a vector x, y, z, what we would be converting into cosine theta, sine theta, and z. right? That's what that essentially gets converted into. So what we're going to do now is take partial derivatives with respect to theta of each entry. If we do that, so that's kind of what this r theta means. So we would get sine theta for the x entry. We would get cosine theta for the y entry, and we would get 0 for the k hat entry. Now, for our z, well, we would just end up getting 0, 0, 1, right? The derivative of this would be 0, this would be 0, and that would be 1. Okay, so that's the idea there. Now, we just have to find the cross product. So we get I hat times cosine, and, well, that's really going to be the only I hat entry. We're going to get minus j hat times, the only thing that we're going to have there is a negative sign, and then with k hat, well, that's just going to be 0. So we really just end up with cosine theta negative, not negative, because there's two negatives there. We'll have a sine theta, and then we'll have 0. So we have to find the magnitude of that. Remember, the magnitude of this vector, let's write that as, we'll just say the magnitude of cosine theta sine theta 0 is going to be equal to the square root of the sum of the squares, essentially. So cosine squared theta plus sine squared theta plus 0 squared, which we can see that that's just going to be 1. So that little piece there ends up really not even mattering for S1, which is really nice. So what we're going to do now is just form the integral. So since that's 1, this piece will go away, right? This piece right here. And we just have d1 z dA, all right? And we have to think to ourselves, what are our bounds again for d1? Well, we wrote them right here, okay? Theta goes from 0 to 2 pi, so I'll write that down. And z goes from 0 to 1 plus cosine theta. So adjusting our dA to be dz d theta, we can begin integrating. All right, so when we integrate, for starters, we'll get a z squared over 2, and then we have to evaluate that from 0 to 1 plus cosine theta, with the d theta on the end. Okay, now what this ends up becoming is the integral from 0 to 2 pi of a 1 plus, this will just be a 2 cosine theta plus cosine squared theta. And this will be over 2, so I'll just put a 1/2 out here and call this d theta. Okay, so now we can just go through and integrate this, and to integrate the cosine squared theta, I'm going to rewrite it here as 1 plus cosine of 2 theta over 2, and you guys have seen that before, right? Which, and I'll make another line because I don't want to keep editing in case you are writing in pencil, which I assume most of you are. This will be 3/2 from the 1/2 right here, plus 2 cosine theta plus cosine of 2 theta d theta. Okay, and integrating here, we're going to get 1/2 times 3 theta over 2 plus, we're going to have a 2 sine theta plus a sine of 2 theta over 2. All right, and we evaluate that from 0 to 2 pi. Now you can see that the signs are going to go away here. They're not going to matter. And, well, we're just going to have a 1/2 times, and the 0 also will make the signs go away. So we have a 3 times 2 pi over 2, which gives us a 3 pi over 2. Okay, so that is S1. All right, and now it's going to be time to move on to S2. All right, and S2 will not be nearly as difficult, and here's why. For S2, we would need to set up a double integral for z ds, but this is not d1 anymore, this is d2. Thing about d2, right, or well, S2 in general, is that it's spanning the z equals 0 plane, right? And well, that just means that if we were to parameterize this in a similar way, or in the exact same way rather, our z bounds would go from 0 to 0. So we call this this would be dA, not ds, but we would say dz d theta and have from 0 to 2 pi, right? Well, that just means that the answer to this will be 0. Okay? And then we can continue and move on to S3. All right? But S3 is not going to be so nice. Here's why. Our surface is going to be it's going to be difficult to find our bounds. So we're going to have to use that other equation that we talked about. Okay? We won't use the parameterization that we recently did for S1 and S2. So what we're going to do here is we're going to use polar. Okay? Because we're going to, and I'll highlight this. Okay, this is what I'm talking about doing. Okay? So we're going to be using polar to represent z as a function of x and y in a way, right? So we're going to write x as r cosine theta. We're going to write y as r sine theta. And we're going to write z as a function of x and y, right? And, well, remember, S3 is that plane 1 plus x. So z is already a function of x and y, but I mean, you can say it's just a function of x, that's fine, but really, z is 1 plus x. So we can write that as 1 plus r cosine theta. So this is equal to 1 plus r cosine theta. Now that we have this down, well, what we can do is end up plugging in, right? We have the double integral of S3 z ds is equal to the double integral of d3, right? And we have f of xy, g of xy, times the square root of dz dx squared plus dz dy squared plus 1. That's also under the radical, and we have dA on the end. So now let's start subbing in here. Okay? We'll work on our d3 in a second here, but I want to get the integrand out of the way. That function of xy and g of xy, that's just z, right? Z is, well, 1 plus r cosine theta, right? 1 plus r cosine theta. And then we have multiplied by that square root of dz dx plus dz dy. Now, I just wrote up at the top here that z is equal to 1 plus x, right? That's where we got the 1 plus r cosine theta from. So taking derivatives of that with respect to x and y is how we're going to get the square root, right? In which case dz dx would be 1, dz dy will be 0, and then we'll have a plus 1 there. And then we'll have dA. dA, remember, that's going to be r dr d theta since we're in polar now. Okay? And the bounds for our double integral, well, theta will go from 0 to 2 pi, right? And for r, that's going to go from 0 to 1. Okay? And I'll show you that region, right? S3, r will still go from 0 to 1. Okay, and you also have your theta, which goes completely around S3. Okay, so cool. Now, moving on, let's combine this here and make this a little nicer. So we're going to pull out a rad 2 that comes from here, and we have 0 to 1 we have r plus r squared cosine theta. And then we have a dr d theta. We'll integrate for our first round, and we'll have rad 2, the integral from 0 to 2 pi, of r squared over 2 plus r cubed over 3 cosine theta evaluated from 0 to 1 d theta. We'll get a rad 2 times the integral from 0 to 2 pi of a 1/2 plus a 1/3 cosine theta d theta. And we'll integrate again to get rad 2 times theta over 2 plus a sine theta over 3 evaluated from 0 to 2 pi. And then, well, we just plug in 2 pi for the thetas, then we plug in 0 for the thetas, the sine goes away pretty much. The only thing that ends up mattering is this piece when we plug in 2 pi. So we get rad 2 times 2 pi over 2, which gives you pi rad 2. Okay? So now, all that's left to do is add up all of the integrals that we got from S1, S2, and S3. Okay, we do that, and, well, the only thing we have to really worry about is S1 and S2, right? So we have a 3 pi over 2 up here, and we have a pi over 2 down here. 3 pi over 2 plus pi over 2, right? So 3 pi over 2 plus pi rad 2, right? And that's our answer. Okay, so that is essentially what this integral equals. And you can even write that as the double integral of S z ds equals that, right? And you can go and write that. Okay, so that's our answer for that guy. All right, so now we're going to move on to Stokes Theorem. All right, now Stokes Theorem is another difficult one, okay, and I'm going to be completely honest here, I definitely had some difficulties with Stokes Theorem as well, because while Greens Theorem and, you know, like all the other line integral stuff that we've done have been really nice, Stokes Theorem, not super nice in most occasions, okay, so let's go through and see what it is. So with Stokes Theorem, it's basically a 3D Greens Theorem, okay, and remember for Greens Theorem, we had a vector field, and the components of that vector field was P and Q, and we were basically relating a line integral in 2 dimensions to a plane region, or to an integral over a plane region, right? Well, now, with Stokes Theorem, we are relating a line integral in 3 dimensions, okay, so our vector field is now in 3 dimensions, so it'd be like PQR, right? And we're relating that to a surface integral, okay? And I'm not going to talk too much about that. Also, my apostrophe is in the wrong place. So yeah, we have a surface integral of the curl of f dot ds. Okay, so that's the idea with Stokes Theorem. So now we're doing another surface integral, but we're doing it with the curl of f as our integrand. So now let's move on to our example here, and we want to find the integral over c of f dot dr, where c is rotated counterclockwise from above, and we have f and c below. F of xyz is xyi plus yzj hat plus xzk hat, and c is the boundary of the part of the paraboloid z equals 1 minus x squared minus y squared in the first octant. From this problem, me reading this, you can see how much I don't like Stokes Theorem. Like, it is honestly a big pain. It's surface integrals, you know, so it sucks. But all right, enough. Curl of f is the gradient dot f. No, it is not. It cross f. So what we're gonna do is set up our matrix. So we have I hat, j hat, k hat. We have our del operator, ddx, dy, ddz, and we have the components of f, which are listed over here. We have xy, yz, and xz, and let's find the determinant of this 3 by 3. We have I hat times we'll have ddy of xz minus ddz of yz minus j hat times ddx of xz minus ddz of xy plus k hat times ddx of yz minus d dy of xy. So this is all going to equal the partial derivative with respect to y of xz is 0. Okay, and then we have minus, this will be y I hat minus j hat times, we'll get a z minus 0. We'll get plus k hat times, this will just be 0 minus a x. So our vector, our curl of f, is negative y, negative z, negative x. So we have the integral over c, and we know from Stokes Theorem that this is equal to the double integral, okay, the double integral of s of the curl of f dot ds. Okay, so we know the curl of f, okay, and we can rewrite this as the double integral over s of negative y, negative z, negative x dot ds. Okay, so what we need to do now is use a surface integral formula. Okay, and this is probably, I guess this is a formula that I didn't mention earlier, so you do want to jot this down. Okay, and this is the double integral of d, we have a negative p times dg with respect to x, minus q dg dy plus r, and then we have a dA on the end. Now g is our c, right? It's our c function, okay? So remember, c was 1 minus x squared minus y squared in the first octant. Okay, so that is g of xy. Okay, now dg dx is equal to, you can see that's equal to negative 2x, and dg dy is equal to negative 2y. All right, so we're going to write this double integral now below. D, we have negative p, which we know to be y, right? We're getting that right from here. Y times dg dx is negative 2x. We have minus q, right? But so that'll be a z, be plus z. And then we have dg dy, which is negative 2y. So actually that'll become a negative again. Okay, and then we have plus r, which is minus x. Okay, and we'll have dA on the end. Okay, now the thing is, this is a double integral, but we have 3 variables in there. We have an x, a y, and a z. So what we're going to do is we know that z equals 1 minus x squared minus y squared, right? That's what c tells us. So we're going to be plugging that in our integrand. Okay, so we're going to have double integral over d of negative 2xy minus a 1 minus x squared minus y squared times 2y minus x dA. Now before I actually go through and distribute once more here and kind of really simplify this down, the problem here is that our bounds are going to be, what are they even going to be? We're talking about a paraboloid here. What we can do right now is convert to polar, okay? And if we convert to polar, things will get a lot easier. And the reason why I didn't simplify all the way here is because we have an x squared plus y squared, essentially. I mean, we have a negative x squared minus y squared. We could just make that a negative r squared right now. So I'm not going to distribute further and then have to take that all apart. Okay, so if we converted to polar here, we would have the double integral over d, and we'll figure out what those bounds are in a second, of negative 2 r cosine theta, r sine theta, minus a 1 minus r squared times 2 r sine theta, minus, we have a x, so this is r cosine theta. We have r dr d theta. So since we're taking into account our paraboloid here, okay, in the first octant, we know that theta is going to go from 0 to pi over 2. Okay, that's the first octant, right? And then our r is going to be going from 0 to 1. All right, now we can begin integrating after we simplify. 0 to pi over 2, 0 to 1, and we have a negative 2r cosine theta, r squared, but that will actually become an r cubed because we have that r on the outside. So r cubed cosine theta sine theta minus a 2r squared sine theta plus a 2r to the 4th sine theta minus a r squared cosine theta dr d theta. Now we can integrate. We get 0 to pi over 2 of a negative r to the 4th over 2 cosine theta sine theta minus a 2r cubed over 3 sine theta plus a 2 over 5 r to the 5th sine theta minus r cubed over 3 cosine theta, evaluated from 0 to 1 d theta. And we can now evaluate that. We'll just get negative 1/2 cosine theta sine theta minus 1/3 sine theta plus 2/5 sine theta, and then minus a 1/3 cosine theta d theta. So we can combine the two signs right now, or we can do it later. It doesn't matter. We can also combine this using a trig identity, so we don't have to do any other methods of integration. We can rewrite this as a negative 1 over 4 times sine of 2 theta minus 1/3 sine theta plus 2/5 sine theta minus 1 over 3 cosine theta d theta. Okay, and integrating here, we will get a cosine of 2 theta over 8 minus, well, actually plus cosine theta over 3. We'll get plus, no, we will not. Jeez, messing up the signs. 2 cosine theta over 5, and then we'll have minus a sine theta over 3, and evaluated from 0 to pi over 2. Okay, when we go through that evaluation, what we will end up getting, and I'm kind of just done doing math right now, so what we're going to get is a negative 17 over 20. So, and you can verify that yourself. But I'm kind of running out of time for what I wanted to do for this video, so we gotta get going here. All right. The last thing that we're gonna cover is divergence theorem, and divergence theorem was like the nice little break at the end of vector calculus, because I was like, after all like the disgusting surface integrals, Stokes theorem stuff, it was divergence theorem, and I was like, oh, this is so much better. Okay, so here's what divergence theorem is. It's basically Greens theorem in vector form. Or it stems from Greens theorem in vector form. So with Greens theorem in vector form, you start out with a curved, with a line integral over some curve C, and it's of f dot ds, right? And f is a vector field. And if you can set that equal to, with Greens theorem, the double integral over some planar region D of the divergence of f. Okay, and what the divergence theorem does is it basically just has a surface integral on one side, right? So you're kind of like integrating each side one more time, right? And you have a surface integral, but you can express that as a triple integral using the divergence theorem, okay? And that becomes really, really nice. So basically it's relating a surface integral to a triple integral, like I just said. And why do we do that? Well, the integration gets much nicer, and you'll be able to see that here. So we want to find the flux of the vector field xyz out of x squared plus y squared plus z squared equals 4, and I have the divergence theorem written again down here. Now you'll also see the divergence theorem written with a closed integral sign. If you're talking about flux or something like that, you're talking about a closed surface. What we're going to be doing is writing the surface integral of xyz ds. We'll write it as the triple integral over E of the divergence of xyz, okay, times dv. All right, and if we find the divergence of xyz, so we can just do gradient cross f, no, not cross f, dot f, okay, and well, that becomes the partial derivative of x plus the partial derivative with respect to y of y plus the partial derivative with respect to z of z, which will end up giving us 3, right? And the nice thing about this problem is that, well, if you set this up, you just have the triple integral over E of 3 dv, right? But the thing is, we can factor out that 3, right? And you know what the volume of this sphere is, because we have a sphere, right? So instead of converting the triple, or not triple, instead of converting the spherical coordinates, we can just find the volume of this sphere, okay? The sphere is of radius 2. So this is 3 times 4/3 pi r cubed. And when we plug in 2 cubed, right, this is just 4 pi times 8, which, well, that gives you 32 pi. Okay, so that's a quick little way to do divergence theorem. And now you're not always going to have a sphere, right? A nice little sphere. That was kind of for the purpose of finding the flux. It's nicer to have a sphere. I'm kind of thinking in terms of Gauss's law, but that was really nice compared to something like Stokes theorem or surface integrals, right? And I know I gave you a much easier problem for divergence theorem than I did for Stokes and surface, but you get the point. Okay, so that's going to be it for this video. I really hope you guys do well on your Calculus 3 final. I hope I was able to help you review in an efficient and a good way. If you have any suggestions, leave them in the comments down below, and make sure to subscribe, because this video has taken weeks to make. So yeah, your support is much appreciated. Thanks for watching, and I'll see you soon.